So we are going to start with a chapter on buckling. Okay. Now before we can actually get into buckling, all the equations, and there will be lots of equations, I want you to free up your mind and tell me what you understand by buckling. Have you come across this word? Have you ever seen this in action in your day-to-day life? Anything like that? Sorry? Metro pillar. Acha, okay. All right. In school, have you studied the railway tracks bending out of shape because of thermal expansion? So that is the logic that is usually given, right? That you have to put little gaps in between the railway tracks, between long stretches of the railway tracks. Otherwise, when they thermally expand, these axial forces develop, and that can reduce, induce some sort of a bending of this thing. Okay, so that is not pure buckling in the way that we understand, but some form of buckling. Acha. In school, have you done this thing? I think we have all done this, right? We hold this ruler in between our hands, and then if you press it like this, this kind of a thing, and eventually you'll manage to break it. Okay, so you do like this, so it bends out of shape, right? Now please note that this kind of a deflection that you are seeing, it is certainly bending. It is certainly bending. There is no doubt about it. But this bending is a little bit different from the kind of bending that we have learnt earlier. Meaning that what I have over here, if you see, if I just press down here, what is this? This is a cantilever beam, right? Okay, this is a cantilever beam. Here, the load is actually transverse in direction to the longitudinal axis of the beam. So there is actually a transverse load which is inducing the bending. But when we are doing like this, there is a little bit of a moment, because I'm being very clever in holding my hand in a certain way so that a little bit of a moment is applied. But the majority of the force that I'm applying is in the axial direction. And as a result of this, this is going like that. So try to understand that this buckling is a very special kind of phenomena. And it falls under the very broad category of mechanical phenomena, which is referred to as mechanical instabilities. Okay, so buckling is one form of mechanical instability. Now, which means that there could be other forms of mechanical instability. Now, those other forms could be something like wrinkling. Okay, so wrinkling, if you, so wrinkles of the human flesh as people become older, that is certainly one example. But as a baby grows, okay, baby grows means inside the mother's body, the embryo, okay, one of the first organs to develop is the brain. You perhaps know that, right? The head first develops. And as the brain grows, there are different kinds of folds which appear in the brain. So you look at a fully developed brain, it is full of wrinkles, right? Okay, there are deep ridges. Okay, it's like like a very rocky kind of thing. They're very smooth, okay, but deep ridges and all these things, curves and everything are there. Now those actually develop, those morphological forms are developed during the development of the baby. Okay, and that is one of the prime functions, like that is absolutely crucial to the functioning of the brain. Without those ridges, our brain will not function properly. Okay. Similarly, if you look at the like the little very cute fleshy parts of the arms and thighs of a little baby, you will see that there are some kinds of crease kinds of things. Okay, so our hands don't have those kinds of things. Okay, but like a little baby will have these nice creases. So it looks very cute looking. So those are also some forms of mechanical instability. Furthermore, beyond human and animal life, in the plant life also, you will see very nice examples of these morphological forms appearing. Morphological means basically some kinds of shapes. They are developing because of these mechanical instabilities. We have all seen this. For example, if you take a leaf, just observe a leaf. We don't usually observe these things, but you take a leaf, plant leaf, and you look at the edge. The edge is somewhat like this. Furthermore, if you look at the periphery of the petal of a hibiscus flower, because it is very pronounced there, so you'll almost see it like this. Very pronounced rippling waves like kinds of things are there. So these are also developed as the flower grows or the leaf grows because of mechanical instabilities. Okay, so mechanics is there in the human body, in the animal body, in the plant body also, and these are crucial to the development of these various parts. Okay, and certainly in various kinds of advanced technology also, these are important. For example, my PhD student is sitting here. So day in and day out, he is, grappling with buckling. Okay, that is one of his main things. And believe it or not, the scale at which he does these things, it is, so this is all mathematical modeling. So he does this at the scale of like the length. So this length is what? 30 centimeters, one foot. So the kinds of things that he works on, that is on the order of a few microns. Okay, microns means 10 to the power minus 6 meters. Okay, and that is the larger dimension. The thickness is actually something on the order of few hundred nanometers, and there also we find that buckling can occur. Now, in what context is this? This is in the context of, this is my research area. This is in the context of lithium-ion batteries. Okay, so in the next generation lithium-ion batteries, we have new materials like silicon, which grows immensely in volume. And when these things grow, they have a tendency to buckle out of shape. Okay. Furthermore, if you look at various kinds of sheets, okay, like flat members which are used in civil engineering constructions, there also, because of compressive stresses, you will see that those things can buckle out of shape. Now, this is like, this entire area of buckling is very, very fascinating. Mathematically, it is very, very challenging. But nowadays, what people are trying to do is, they don't always look at buckling as a kind of structural failure. What they're trying to do is to exploit buckling as an architectural advantage. Now, we'll not go into all of these things. We'll not go into plant and animal life, and certainly not into brains. But I'm just trying to give this to you as a motivation. Okay, so this is just like the A of the ABC of the entire alphabet. Okay, so learn this well. If you get interested, there's a whole world out there for you to explore and do advanced studies in. Okay, so all right. So we'll start with the chapter on buckling. The first thing which we'll look at is not directly the elastic bodies that we have been looking at till the previous chapter. Rather, we'll go back to the thing which we have learned in our class 11 and 12, and what you have learned in your third semester in dynamics, basically rigid bodies. Okay, so in the case of a rigid body also, we can have some kind of an instability. Okay, so probably you have already come across some kind of instability, the mathematical representation of instability in terms of an example where you looked at the stability of a ball lying on a concave surface or a convex surface or on a flat surface. Okay, so the overall idea will be connected to that only. Okay, so you will see. So what we'll do is, as a first representative example, we will consider, let's say this. There is a rigid member, there is a hinge here, and here there is a spring. This is a spring. Okay. Yes. And the load here is actually like this. This is the load. Now, as it is written, you will probably think that nothing is going to happen because it is a rigid member. You do not even expect it to shorten in length because that is the definition of a rigid member, right? So nothing interesting is going to happen. But suppose I tell you that what I will do is, through a very, very small force, I will just poke it and I will disturb it from this position. Now, in that disturbed position, let us investigate what happens. And this will be the hallmark of all buckling studies. Okay, we'll have to disturb it and then we'll investigate it. Even when we go to mechanically deformable solids, which is what we have been doing it all the while, so things like beams, there also you'll see that we are going to deform it and then we'll investigate it. Okay, so step by step we'll do it. So we have this kind of a picture. Okay, this angle, this is theta. This force is still vertically downward. Okay. Now you tell me, if I want to consider the free body diagram of this and write down the equations and at the same time consider that things are in equilibrium, then what is going to happen? Suppose what I'll do is, I will take the moment balance about this point. Okay, so let's say this point is O. So sigma MO equal to 0. This is what I'm going to write. What will this give rise to? Let's say that this length is L. Then what is the moment arm for this force P? For the moment balance about this O, what is that? L sine theta. Okay, so this is L sine theta into P. Let's say that the spring constant for this torsional spring is K. Then what will be the minus K theta? Now, remember what I said earlier, that the disturbance is going to be very, very small. Very, very small disturbance means what effectively in mathematical terms? That our theta is small. Okay, so for small theta, what we are going to have effectively is this PL theta is equal to K theta, or P is equal to K by L. Now there is an entire story behind this. Story is like this, that I have written this as static equilibrium. Okay, I am actually saying that this is in equilibrium. Meaning what? That when I disturb it like this and it is in this deflected position, then this force, whatever its action is, and this spring, whatever its action is, they are cancelling out each other, so that this deflected shape is at peace with itself. Right? It does not have a tendency to go either this way or this way. Okay, this is very, very important. It may seem very obvious to you, but it has tremendous importance. It does not have a tendency, if this condition is true, if P is equal to K by L, then it does not have a tendency to go either this way or this way. Furthermore, you note another very, very important thing. I have not defined what theta is. Theta could be 1 degrees, theta could be 2 degrees, or theta could be 1.757 degrees. Doesn't matter. Whatever the theta is, as long as theta is relatively small, this condition is going to hold true and we are okay. We'll say that whatever the theta is, it will be at peace with itself. Okay. Now, as opposed to this condition, suppose I say, no, this is not the condition. Rather, what I have is P is greater than K by L. Now, P is greater than K by L is going to arise only if this L sine theta P is greater than K theta. That is the source. So, this P is greater than K by L. But now you tell me P greater than K by L, what is the significance or what is the implication? This position will not be at peace with itself. Rather, the tendency is that if I disturb it a little bit, it will have a tendency for the theta to grow. Okay, if I disturb it a little bit, the situation is such, because P is greater than K by L, the theta will have a tendency to grow. Okay, the opposite situation is this, that P is less than K by L, which will happen if L sine theta P is less than K theta. In that case, what is going to happen? So theta has a tendency to decrease. So if I disturb it a little bit, the situation is such that this torsional spring will bring it back to its original position. Okay, so this is unstable. Okay, this kind of a disturbance or this kind of a situation that arises as a result of the disturbance, this is an unstable situation. This is a stable situation. Stable situation means whatever the original position was, if it gets deflected, it has a tendency to come back to its position, okay, to its original position. That is a stable position. And what is this? This is nothing. So nothing, we give it a name, we call it neutral. Okay, we call it neutral equilibrium. Okay, so this is neutral. This is unstable. And this is stable. Now see, buckling is very rich mathematically, it is very rich philosophically also. Okay, so I will not lose this opportunity to give you some philosophical gyan. So the thing is like this buckling or this instability applies to our human condition also. Okay, so some people are very stable. Okay, if you disturb them a little bit, okay, they may get disturbed, but very quickly they'll get restored to their original equilibrium position at peace. Some people are not like that. If you disturb them a little bit, they will just fly off. Okay, that is unstable. And some are like this neutral thing. They have like attained moksha. Okay, no matter what you do, they are like whatever position you put them in, they are at peace. Okay. Okay, now if you have understood this thing, we may come back to another example of a rigid body thing, but I want to quickly go to the mechanics of solids kind of thing. Okay, and although the mathematical derivation will be quite different and a little bit more complicated than this, but you will see that ultimately the heart and soul will be like this. Now before I proceed, I want you to very quickly give me a connection or just talk it out with me. What is this thing, this neutral, this unstable and this stable in terms of that convex, concave and flat surface with the ball on it? Okay, so I'll draw three pictures. First is this, second is this, and third is this. So tell me, which one of this is unstable? Last one is unstable. Okay, this is the unstable. Which one is neutral? First one is neutral. And second one, of course, is the stable one. Okay. All right. All right. Now, you have all, I mean, at least the mechanical students, you have done fluid mechanics. Okay. You have studied a little bit of turbulence. Okay, little bit. Okay, so maybe the thermofluid science you do not go up to that part. No matter, there are enough number of videos and resources available. Just look up what is the relationship between turbulence and instability. Okay, maybe you remember something like this, that there is a great significance for pipe flow with the Reynolds number of 2000, approximately 2000. Okay, so please be please be very careful about that Reynolds number 2000 thing. Okay, so whether it transitions or it doesn't transition, so it's a very, very subtle concept associated with it. Please look it up. Okay. All right, we will go now to the actual example of a column. Column means that all this while we have been talking about beams. Now beams, usually we have said that they are in this horizontal configuration, though not necessarily, but usually that is the configuration that we have looked at it. Now if you place this same kind of member in the vertical position and put an axial load on it, the beam, then it becomes a column. Of course there are some other distinguishing features of a column also, but this is the general picture that we'll start out with. Okay. So we have this mechanical member. This is a deformable solid. Okay. It is made of a material which is following the generalized Hooke's law. Okay. Now at this end, I will put a hinge. And at this end also, I will put a hinge. Okay. Now I want the situation to be set up in such a fashion that when I apply a load in the vertical direction, this thing remains straight in the general sense. What I mean by that is that the way that I have put it here, if I now put a force here, what will happen? The hinge is not connected to anything, it is just floating. Okay, it is connected here, but it is not attached to anything. Okay, so if you put a force, it will go this way and this way. I don't want that to happen. I want this end to be guided in the vertical direction. So the little trick that I will do here is to put some kind of a block such that that block will be attached to some rollers, and those rollers will be rolling over these kinds of vertical things. And on top of that, there will be a force. So that downward pointing arrow, that is the force P. Just like in the previous example, I had that thing. So there is also a force P. Now, under normal circumstances, if nothing special is going on, what will happen? If you apply the force P, this thing will get compressed. Okay, just like in our tutorial sheet 0. Okay, just axial deformation. But now you suppose that there is a little bit of a disturbance. Suppose I poke it over here. Okay, through a reasonable amount of force, but a very, very small force. What will happen is that it will get deflected. You know this. Okay, it will get deflected. Now when it gets deflected, whether that is stable or not, okay, that is what we want to investigate. Okay, so when I was holding the plastic ruler in between my hands and pressing it down on it, so it was effectively like this kind of a situation only. Okay, so what we'll do is, just like in the previous rigid body member example, I considered the deflected shape. Here also I will consider the deflected shape and I will investigate on that deflected shape. So this is the thing that I will consider. Those of you who are very, very careful will immediately catch me that it cannot get hinged at this location, because when it gets curved, this distance is now less than this. So it should be actually a little bit below. Okay, so if you want to make that adjustment in the drawing that you make in your copy, please do that. I did not do it because unnecessarily it becomes very cluttered. Okay, but the thing is that it will get pushed down a little bit. Okay, now I will consider a cut here. So this is a cut section. We are familiar with how to deal with it. So this is the moment M. There will be a shear force V. Please also note that the way that I set up my coordinate axis, that is very, very important. Okay, what I will do is I will put the x-axis downward like this and the y-axis like this. Okay, please note that in the deflection chapter I used the variable v, now I am using y. Please don't mind. Okay. Now tell me, how much is this deflection? This is at a generic distance x from this origin. At a generic distance x from the origin, this deflection is just y. Okay. Now you tell me, what is the moment contribution due to this P? If I take the moment balance about an axis which is passing through this end, okay, I repeat, if I take the moment balance about an axis which is passing through this cut end, then what is the moment contribution due to P? Py. Okay, Py. So if I write the entire moment balance, it will look like this, that M plus Py is equal to 0, right? M plus Py is equal to 0, which implies that M is equal to minus Py. Now the way that we'll approach these problems is to write the deflection equation only. Okay, we will write the deflection or we'll consider it in terms of the deflection. Okay, you will see in a moment why, what is the benefit of doing it like this. What is M? M is what? In terms of deflection? EI? EI? D square y dx square. Okay? This is equal to minus Py. Now one little manipulation that I will do is to divide throughout by EI. This is something which we'll always do. You'll see again what is the advantage. It's just a mathematical convenience. Now look very carefully over here. This P is a magnitude of force. E is the Young's modulus. I is the second moment of area. Each of these entities is a positive entity. So overall, this P by EI is a positive entity. Okay. So instead of writing again and again in terms of this P by EI, because we have to do a lot of mathematical manipulation from now on, what I'll do is I'll encapsulate this P by EI in a single variable. But in order to depict it, that it is a positive entity, I'll put a square over it. This is a trick that you know from your JEE days. If there is a positive entity, we put a square over it. So therefore, the equation that we are going to get is this: d square y dx square plus k square y equal to 0. All good? Now we have to solve this. Okay, boundary conditions will come later, but we have to solve this. So what does it look like? SHM. SHM. It looks like SHM, except it's not. Why is it not? Because there is no time here. Okay, there is no time here. It is the spatial variable x. Spatial means one which is depicting the space. Okay, it is not time. Nevertheless, the mathematical form is exactly the SHM. So the solution will also look like the SHM solution. Okay, but we'll pretend that we don't know the SHM solution and we'll do it formally. Okay, how will you do it formally? It's mostly the same trick always. Okay, for these kinds of equations, we will say that let the solution form. So assume the solution form by the way, some of you cannot seem to get out of your JE mentality. So unless numerics are there and one answer has to come out which will be there in one of the choices A, B, C, D, man nahi bharta hai. But JE is over. You have achieved whatever you had to achieve. You are now in IIT. So these things are actually going to be important. So in a very materialistic sense, in the examination, you are going to get questions which are like this. Okay, so these derivations are absolutely important. Okay, so please don't fall asleep. So y is equal to e to the power mx. So now, if we put this over here, what will happen? D square y dx square is on this. What will happen? M square plus k square equal to 0. So m will be what? M is equal to plus minus ik, where I is nothing but the imaginary unit. All good? Okay. Now when you have these two solutions, the final solution will be composed of the contributions of both these things. So right now, we are not in a position to investigate whether the thing is stable, unstable, whatever. Okay. You may think that because I'm getting plus ikx and minus ikx, something I'll be able to say, but not yet. Okay. What I'll do is, using the De Moivre's theorem, I will re-represent this in terms of sines and cosines. Okay. So this e to the power ikx is what? Cos kx plus I, and this thing what I'll do is I'll group the cos kx terms together and group the sin kx terms together. This particular combination I will call A, and this particular combination I will call B. So overall what I will have is A sin kx plus B cos kx. This is the general solution. Okay. Now, your natural tendency will be that because A and B are unknown, I need two conditions in order to find out the A and B. Right? There is nothing wrong with your natural tendency. We are going to do that, but you are in for a little bit of a surprise. Okay. So, what will be the boundary conditions? Tell me. Look at this problem. At x equal to 0, what do you have? Y is equal to 0. And at x equal to L, y equal to 0. As simple as that. Both ends are pinned.
L minus delta.
L minus delta. Oh, that will neglect. Okay. Because this disturbance is very, very small, right? So at x equal to 0, y equal to 0. So what happens? if you put x equal to 0 in a sine kx plus b cos kx, what happens? You get this, b is equal to 0, because a sine 0, that is 0, and b cos 0 is b. Okay, so this is 0. So next, at x equal to L, y equal to 0. What do I get from this? Let me write it properly. A sine KL plus b cos KL equal to 0. But b is 0. Okay, but b is 0. So what I'm left with is a sine KL is equal to 0. Now you all of you pause a little bit. Okay, you think with me. What can I conclude from this? A sine KL equal to 0. See, if I didn't know better, I would say that a is equal to 0. Okay, I would say a is equal to 0. And would I be wrong? No, I'm not going to be wrong. See, you try to think physically. If suppose I claim that a is equal to 0, am I violating anything physically? Because if a is equal to 0, b was already 0, what happens to my general solution? The y is equal to a sine kx plus b cos kx. What happens to it? All of it goes away, and my general solution, it boils down to y is equal to 0. Is there anything wrong with it? What does y equal to 0 as a general solution mean physically? You look at this thing. Okay, you look at this thing, you are pressing down on it from the top, and you are getting as a solution the deflected shape in general to be y equal to 0. That is not wrong. That is very boring, but it is not wrong. Okay, so there is absolutely nothing wrong physically with it. In fact, if you just press down on it, and we were not studying the buckling chapter, that is what you would be expecting, right? If you were in the chapter of axial loading, you would expect that no deflection is taking place. So y is equal to 0 is a perfectly valid solution, except that it is the trivial solution. Okay, it is a boring solution. We are not interested in that. We understand that it exists. It is very much correct, but we want to go beyond that. So what we'll say is that, what are the conditions under which we are not going to have trivial solutions? Okay, so for non-trivial solutions, sine KL equal to 0. What is the implication of sine KL equal to 0? What is the value of n? N is equal to 1, 2, 3, all these things. Okay, we are not going to put n is equal to 0. Okay, that is acceptable, but that is also a trivial thing. So n is equal to 1, 2, 3, all these things. Now, what does this k contain? Remember what k was? K was equal to square root of p by ei. Okay. So what I'll do is, I'll write this as k square. So this thing that we are obtaining, This seems to be very curious. What is it telling us basically? Can anyone tell me? What is it telling us?
Based on the given load, it will adjust itself. Some sign.
So it is telling us that suppose you take n is equal to 1, then P will have a certain value which will be equal to pi square EI by L square. For that particular value, I am going to get a stable solution which will be deflected like this. Okay, I'll get a stable solution which will be deflected like this. Let us not forget what was our original solution. It was y is equal to a sine kx plus b cos kx, where b is equal to 0. So this thing is a sine kx. Do we know what a is? We have only said that we will not allow a to be equal to 0. But what a will be, that we have not decided. And we have no other way of finding it out. That is how it is. So a remains undetermined. You write this. This is very, very important. That a remains undetermined. Now, this particular form, if I substitute the value of k over here, what is the first value of k? You look from here. This is pi by L. Okay, because n pi by L, no? N pi by L, first value is n is corresponding to n is equal to 1. Okay, so for n is equal to 1, what I have is a sine pi x by L. Is it not? Does it satisfy the boundary conditions? You put x equal to 0. Is y equal to 0? Yes. You put x equal to L. Is y equal to 0? Yes. So the boundary conditions are satisfied. However, it is in the form of a half wave. So if you consider the sinusoidal wave, then this is the half wave. Okay. So from 0 to pi, whatever it is, that is what it is. Okay. But you do not know what the amplitude is. So this A is undetermined. Now compare with the previous thing. When theta was something, whatever that 1 degree, 2 degree or 1.757 degree, whatever it was, okay, it was a stable solution. In the same way, this thing is also a stable solution irrespective of what A is, as long as the deflection is not too much. Okay, this is what it is telling us. But in addition to the previous consideration, now we have different orders at which this is true. The first thing is for n is equal to 1, which is what I have written. But suppose now you choose n is equal to 2, you are going to get a different shape. Okay, so these things that you are obtaining, these are, you are actually familiar with this. These are referred to as what? These are the mode shapes. Okay, these are the mode shapes, just like in waves you have. Okay, so these are the mode shapes, right? Now, this entire thing that I have done, okay, this entire thing that I have done, you tell me, does it remind you of anything? Huh? No, in terms of differential equations is fine, but in terms of your, so all of you have done the linear algebra course, right, in first year. Does it remind you of anything of that? Here. Nothing, right? Nothing. Okay, we'll see. We'll explore whether there is nothing or something. But before going forward, I need to write down something very important, which is that for this n is equal to 1, this P is equal to pi square EI by L square. This is a very, very fundamental case. Okay, this is a very, very fundamental case. So remember that this solution that you are obtaining for the different values of stable P's, okay, this corresponds to this situation where both the ends are pinned. Subsequently, after this, okay, just after this, we are going to consider other kinds of boundary conditions. and then you will see that that is no longer going to be true. But it is historically important, and it is also important in terms of structural analysis. Okay, because many kinds of joints, they can be actually modeled in terms of these spin joints. Okay, so this is actually referred to as the Euler's buckling load. Euler's buckling load or Euler's critical buckling load. Okay, and this is the fundamental case. Fundamental means corresponding to n is equal to 1. Okay, so please write this down. And this is the same Euler that you are familiar with, Leonhard Euler. Okay, and he did this, I don't remember the date exactly, but somewhere in the 1740s and 1750s. Okay, so this is one of the earliest mechanical formulas that are there, the formal mechanical formulas. Okay, now that you have understood, kind of understood this thing, we'll go on to the next case. Okay,